So welcome back to the contributed talk for the session 8 of the conference. Today we're going to have two talks, and the first one I'm happy to introduce to you Álvaro Gutiérrez from the University of Bonn. He's going to talk today, if I'm not mistaken, about representation of general linear groups, and more specifically, where are plethystic coefficient non-zero. So Álvaro, to you.
Yeah, okay, thank you for the introduction, and good morning, good afternoon, or good evening, depending on where you are. So yeah, as he said, the title of my talk is "When are plethystic coefficient non-zero?" And here the B word is this one, right? The weird word. So I'm going to spend most of my talk trying to motivate what this word means. Also, the slides will be available in my webpage. So if you're seeing this in the recording, you can download them. Okay. Oh, so I see in my second monitor that you are seeing everything shifted. Is that right? Is the word plethystic being crossed out by my drawing?
A bit, yes.
Okay, I'll keep that in mind, yeah. I guess. Okay, so I have to. Yeah, so the motivation is going to be studying some trees, some combinatorial objects, in this case trees. And in algebraic combinatorics, something you do is to associate an algebraic structure to a combinatorial structure, right? So one object that we can associate to a tree to understand its structure, or in this case, only the leaves of the tree, okay? It's going to be the group of symmetries of the given tree. So we have here two different trees with two different group of symmetries of their leaves. But one key realization is that one can break this problem up into smaller problems, right? So in the left tree, for instance, we see that the group of symmetries is going to be the group of symmetries of the left part of the tree times the group of symmetries of the right part of the tree. And again, for the right part, we can further decompose it. So we now have that the group of symmetries of the bigger tree is the product of three smaller groups. And we can also just compute those groups. So what's the group of symmetries of this? So it's just going to be S3, right? Because no matter how I permute these leaves, it leaves invariant the structure of the tree. And similarly, for the other two, they are S1 and S2. Okay. Now for the right tree, the story is a bit different, because it's true that we have symmetries of this part and this part independently. So I can permute these things and I can permute these things independently, but I can also preserve the shape of the tree by permuting these two blocks. So we have sort of a symmetric group inside of symmetric group. Oops. So what I mean by that is that the automorphisms of this tree is going to be the automorphisms of this smaller block, red product, S2, because sorry, that's an H. Red product with S2, because we can sort of imagine it's a tree like this. Inside of each blob, now we have a smaller tree. Okay. And again, I can finish the story just by saying, well, the automorphisms of this part is S3. Okay. Now, in representation theory, we normally look for more structure. So right now we can study these trees with some groups, which is this left world. But in representation theory, we like studying groups with vector spaces. And so we associate to this group this vector space. And if you are combinatorialists, then you maybe prefer giving like studying representations with symmetric functions, which is this world right here. And this map is really nice. So you can go forward and backwards most of the time. And there's two ways of going from the group to the right world. You either go with inducting a representation, blah, 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 or with Polya's zeta function. And this is called Frobenius characteristic map. Okay. But the important thing here is that the weird operation of groups, of having one group inside the other group, which we call the ref product, is translated to composition of representations. So these are representations of CL. Well, L is the group of leaves, but there's a good understanding. It's well known that representations of a finite of a module like this are just representations of GLN. Okay, and a representation is a map from a group to some GLN, so GLV, and if this group is in itself a GLW, I can just compose these representations. I don't know, I ran out of letters, GLU. So now this is another representation, which is the composition of these two representations. And in the world of symmetric functions, this operation of composition gets translated to plethism, which this word comes from Greek, and it means product. But for us, the symbol is reminiscent of that of composition, rather. So again, ref translates to composition, translates to plethism. And this translation is good in the sense that in representation theory, we normally want to study representations by breaking them up into irreducible representations, as shown in the formula. Each irreducible representation is indexed by a partition, and each irreducible representation appears a number of times, which I call this A coefficient. Okay, so again, in representation theory, we normally want to know how to decompose a representation into irreducibles, and so we want to study these coefficients right here. And this translation, this CH, is really good in the sense that it preserves these coefficients. And now the question is equivalent to say, how does this plethism break up as a linear combination of Schur functions? So these S sub lambda are Schur functions. This one right here is a Schur function. This is a Schur function 2, and this is a Schur function 2. Okay, I will say what a Schur function is briefly in a bit. By the way, we can also do the same thing with the other type of structure, so with product, and the product of the groups here would translate to tensor here and to regular product here. And then this map is good also in the sense that the tensor of representations, now with these coefficients that I call C, translates to the product of representations. And again, this structure is, so the question is equivalent to say, how does this product of two Schur functions break up as a linear combination of Schur functions? Okay. So what are symmetric functions? Symmetric functions are formal power series in a countable number of variables and invariant by any permutation of its variables. So maybe the easiest examples are these power sum symmetric functions. This one is evident that permuting any of the variables doesn't change the sum. And likewise, this one is also symmetric. And these functions, these Pn, generate the algebra of symmetric functions. Maybe a more complicated example would be Schur functions. So Schur functions are indexed by partitions, This is a partition of 2, which is just 2 equals 2. And this is a partition of 3, which is 3 equals 2 plus 1. And I represent this by drawing 2 boxes and then 1 box on top. Okay. Sure functions are defined as the generating functions of tableaus. So a tableau is a filling of this partition diagram with some restraints. And so if I take this partition diagram and I fill it in all the ways possible, and then I take, for each of these tableaus, I take one monomial, I generate the Schur function. And similarly here, these 2 correspond to this monomial, this one corresponds to this monomial, and this one corresponds to this monomial. I bet you can see more or less how this works. And Schur functions are a basis of the algebra of symmetric functions. So they are a basis as a vector space. So it makes sense to ask, how does a random symmetric function decompose as a linear combination of Schur functions? But I'm gonna get to the point, and the point of this talk is just announcing some results that me and my advisor at the time during my bachelor got with these coefficients that I introduced, these A's and C's. So the main result that we got is that the plethism, so if the plethism of 2 Schur functions breaks up into a linear combination of Schur functions with these coefficients A, lambda, mu, nu, so this coefficient is non-zero, implies that nu, the little one here, is inside lambda. And to illustrate this, I have here a coefficient that is non-zero, and you can check this with Sage, for instance. And you can see that this guy fits here just by, maybe I do it bigger. So this is the bigger one, and the smaller one fits just by doing this. Okay, so when we mean subset, we always identify the top left corner. Oh, I now realize that I haven't been keeping a straight convention. I sometimes draw the partitions like this in the French way, and I sometimes draw it like this in the English way. I'm sorry for that. I hope you can pardon me. So yeah, this is our theorem, and maybe I should say why this is relevant. So plethystic coefficients are not well understood at all, but even Littlewood-Richardson coefficients, which are the ones that, so the other ones, these ones are well understood, and even for them, it's really hard to say when is this non-zero. And for Terence Tao with Allen Knudson showed the saturation conjecture, which was a conjecture in stability behavior of these coefficients, and that involves these coefficients being non-zero. Namely, if a coefficient is non-zero, then the next ones, like multiplying here by n, is also non-zero. So it's a big deal in representation theory to understand when are these coefficients non-zero, and it's an NP problem. So it's not hard it's not easy to develop algorithms or ways to figure out when is this behavior happening. Another result that we got is that, so we had 2 intermediate results to get to this that are also relevant in their own. The first one being what happens if you do the plethism of a power sum symmetric function with a Schur function. Then these coefficients are non-zero, again, if nu fits inside lambda. So it's a very similar statement for a different question. And finally, we had another result that involves these Littlewood-Richardson coefficients, but generalized. So imagine the product of many sure functions, k sure functions. In the beginning, we had a tree that was like this. Whoops. Okay, so this one had 3 sure functions. If you recall, this one would give S3 times S1 times S2. These are really easy sure functions because they are just indexed by a row partition, but they are sure functions. So imagine you have a product of k of those with some coefficients. They decompose into a linear combination of sure functions. And now, whoops, let me follow an example. Let's take mu equals to this, mu0 equals to this, mu1 equals to this, and mu2 equals to mu1. And we now compute their exterior corners. So this means, for instance, this first one, mu0, is this shape. So the exterior corners are the guys that we have to cut out to make this shape. So if we cut out here, here, and here from the from this plane, we find mu0, right? So those are the exterior corners, and I have here the coordinates. Then I do the same for mu1 and mu2, and I have here the coordinates. I then sum all these possible combinations. So I take every possible combination of exterior corner from mu0, an exterior corner from mu1, an exterior corner from mu2, and I sum their coordinates. And I have here in this diagram all the resulting points, and this yields a shape, okay, in blue. And the statement is that if this coefficient, if lambda doesn't vanish, so if lambda appears with a non-negative coefficient, a non-zero coefficient in the product S mu0, S mu1, S mu2, then lambda fits inside this blue region. Okay, and that's it. I have 1 minute, so again, I want to relate this to tiles. So well, no, I guess I don't have any more time. So thank you.
You can have 1 minute too if you want.
Yeah, I was just gonna say a bit more about how this is relevant, because, like, again, for instance, turnstile proof that if if this coefficient is non-zero, then this other coefficient is non-zero. So just to illustrate that these are non-trivial questions that are really relevant in representation theory, I just wanted to mention again that these results existed. And that's it. Thank you very much.
Okay, thank you, Álvaro. Let's thank the speaker. You can react. Pretty nice. Anybody has a question for the speaker? I don't mind starting. It's not my field, so I'm not an expert, but it's somehow. So you talk about Littlewood-Richardson coefficient, which is like closely related. It's similar also to Kronecker coefficient, no? In what I've seen.
Right. Yes. So Kronecker coefficients are a third different structural coefficient of symmetric functions. They correspond to the Kronecker product of sure functions. And so to see this in representation theory, I think it's also a tensor of representations.
Yeah.
But before we induced this to a bigger group, and now we don't do that, and now we restrict to a smaller group, symmetric group. I think it's that, but like I'm not an expert on Kronecker coefficients either.
I've seen it very briefly, but yeah. Okay. And but I guess you have a condition for a necessary condition for the coefficient to be non-zero.
Mm-hmm.
And have you looked at the computation aspect of that? Is it
okay? Yes. So these algorithms that we present are polynomial, whereas the question is non-polynomial. So necessarily our bounds are not perfect, but we do have let me look for it. We do give an example, an illustrating example that you can find on the literature. So there's a lot. Okay, that was another question. So let me look for it here. So in a paper that it's well known in algebraic combinatorics, it said how there is a priori 230 partitions that could appear in a certain product, but only 40 appear. So from 230 possibilities, so 230 possible triples, lambda, mu, nu, only 40 verify that this coefficient is non-zero.
Okay.
And with our bound, you restrict this to 142.
Okay. So you reduce the space. No, but you reduce the space of what you have looked. Yes. Yeah,
it's not perfect, but it helps. I think this is really recent, so I don't know if it will be relevant in computations, but for the moment. And there was another question in the chat.
Yeah, so Angus asked, so he said this might be a silly question, but in your first slide, you said that the first motivation was studying automorphism of tree. Do these results you and your supervisor got relate back to that?
No, I don't think so, or I don't think it has been studied yet. So when I always start with this, all my talks, because there's a paper by Khan, which is called a representation on labeled root forests. And he introduces how to exactly do that, how to go from trees to representations, and it uses plethism. So it's a very visual way of understanding plethism. But this, again, this is really recent. This is like 2019, 2020. And I think it's more of a way of studying representations with trees and not trees with representations at the moment.
Okay. Well, thanks. Well, is there any more question? We have 1 or 2 more minutes. Okay, so let's thank the speaker again. So thanks a lot, Álvaro. It was quite nice.
Thank you very much.